Big numbers, Brady. A mega and a Mosa.
A mega and a Moser.
A mega and a Mosa. So these numbers, well, a mega goes back to, there's a book that was published sort of in the early part of the last century by Hugo Steinhaus called Mathematical Snapshots. And it was in that book that he introduced the idea of a mega. I'll explain to you what a mega is. It's a very big number. He introduced like a cool notation for generating big numbers. So I'm just going to start with it. So we start with the triangle. So if we define triangle of n, right, which we write like that, then what that means is n to the power of n. So for example, let's just see how that's going to work. It's pretty straightforward, right? So we want triangle of 2, okay? That means 2 to the power of 2, which is of course 4. Which managed to do that, right? If we do 3, obviously that's 3 to the power of 3, which is going to be 27. We can carry on, you know, do as many as we want. 4, that would be 4 to the power of 4, which is actually 256, I think. Okay, so you could carry on like this, right? But this isn't really going to generate very big numbers. So what do you do next? What does Steinhaus do next? Well, from the triangle, we move up to the next polygon, which is, of course, the square. So we define square n. Okay, so what does this mean? Well, this literally means n inside n triangles. So if you were to draw it, you know, you would think it's going to be, you know, it's sort of tricky, right? So you've got an n.
Oh, that escalated more than I thought. I thought it was just going to be like n to the n to the n.
No. This is going to get worse, Brady. This is really going to escalate. So what mathematicians like to do. So we've got n, and we've got it inside a triangle, and then inside another triangle. And there's lots of these triangles. In fact, how many of them? There are n of them, right? Okay, so let's just try a few. So let's try, you know, square 2. Okay, square 2 means 2 inside 2 triangles. Okay, so let's figure out what that is. So we've got 2 triangles. And there are actually 2 different ways that you could calculate this. So let's just try the first way. So the first way, well, we know what triangle 2 is. Okay, that's 4. So we could just directly calculate that. So that's going to become 4 inside a single triangle, which we've already done is 256. That's 4 to the 4. That's one way you could do this. The other way is you sort of just calculate the outer triangle first. So this means that this is going to be triangle 2 to the power of triangle 2, right? Which again is 4. This triangle 2 is 4. So that's 4 to the 4, which again is 256. So it's consistent, right? So you can build like this.
So the 2 ways you can do it give you the same result?
Yeah, 2 ways you do it will give you the same result. So it's consistent. Obviously, you can do square 3, which is going to be a 3 inside 3 triangles.
How big square 3? Square 3 is...
Let's work it out. Well, let's do it, right? Okay. Okay, so square 3 is it's going to be very big. It's a 3 inside 3 triangles. Okay, so it's going to be that. Well, triangle 3 is already 27. Okay, so that's 27 inside 2 triangles. Okay, 27 inside a triangle is 27 to the 27. So this is 27 to the 27, which I'm not going to calculate, inside a single triangle. And so this must then be 27 to the 27 to the power of 27 to the 27, right? This is big, okay? So already you get very big, right? And you can imagine it's going to get bigger and bigger. But we're not at a mega yet, but we're almost at a mega. So let's get to a mega, okay? I'll get a new paper. First, we need the next bit of notation. So we've got this triangle, we've got the square. What does Steinhaus define next? Well, he defines the circle, okay? So he defines the circle, like so, which you can kind of guess what it's probably going to be. It's n inside n squares. Square n was n inside n triangles. A circle, n is n inside n squares.
Why didn't you use the pentagon?
We'll come to that, Brady. No, you're one step ahead. See, you're a very good mathematician. Yes, we'll come to that. But we're not there yet because Steinhaus didn't. He did use the circle. This is obviously, going to generate very big numbers. In fact, straight away, we're going to hit a mega. So what is mega? Mega is defined as circle 2. Okay, so let's figure out what this is.
It doesn't feel like it would be that big.
You don't think so? You don't think, Brady?
Not with 2.
Oh, well, let's see, shall we? This means a 2 inside 2 squares? Well, we just calculated what square 2 was. It was 256. So that means that this is 256. It was square 256. Remember what this now means. 256 inside 256 triangles. Right? So let's do that. So we got 256, right? Inside a triangle. We've got then lots, it's hard to draw, lots of these triangles. In fact, how many of them we've got? We've got 256. So it's 256 inside 256 triangles. It's going to be big, right?
I take it back.
You rightly so. It is big. Okay, how big? It's definitely big.
Definitely big.
It's definitely big. Okay, well we know how big. We've got an estimate for how big. We can estimate it. So it has. We know some bounds.
So it's not even a number we can pin down. Like.
Well, we'll come to that. Okay. Yeah. Can we write it down? Well, the answer's going to be no. But let's see. Okay. So what are some bounds for this number? So this number is less than 2 arrow 260, which I'll tell you what that is in a minute. And it's bigger than 2 arrow 259. Why? Why is this? What does this mean? This means, so this double arrow notation, if you remember from our video in Graham's number where we did define it, but just to very quickly tell you what it is, it basically means a power tower. So if I write 2 double arrow 260, what that means is that's 2 to the 2 to the 2 to the 2, where that tower of 2's is 260 levels high. Okay, so very big number.
That's double arrow.
That's double arrow. Yeah. This, so this we've got 2. So this is going to be 2 to the 2 to the 2. The power tower is going to be 259 levels high. So a mega is bigger than that number. It's not bigger than this number, but it is bigger than that number.
We're still not touching Graham's number sort of levels because that's got even more arrows, doesn't it?
True, it is, but yes, we're nowhere near Graham's number. Okay, but how are we compared to like a Google or a Googleplex? What do you reckon?
I'm thinking bigger.
Bigger than a Google and a Googleplex?
Yeah.
Sure.
No.
You're right, Brady, you're right. It's way bigger. It's actually way bigger, right? So just in terms of what a Google is, if you wrote it in this language, so a Google, obviously we know what a Google is. It's a 1 followed by 100 zeros. If you want to write it in these kind of bounds, then it would actually be less than 2 arrow 5. So it's actually less than 2 to the 2 to the 2 to the 2, where the levels are 5 high. A Googleplex, on the other hand, well, you might think a Googleplex would be loads bigger, but actually a Googleplex is actually less than 2 arrow 6. Okay, so that doesn't even compare.
Isn't mega like associated in physics with 1,000 or 1,000,000 or something?
1,000,000 actually, normally. Yeah. So if you talk about a mega electron volts, that would be which is the mass of the electron. That's a mega electron volt.
Seems like a poor choice of name. Like, or am I being unfair? I know mega also just means, massive.
Massive, right? Yeah. I mean, I don't know. Actually, I guess you have to have that fight with Steinhaus. He's the one that picked the name. What do we know about it? Right. So surprisingly, not that much because it is. I mean, you can sort of write. I mean, certainly we can't write it out in full. I did read somewhere that it was speculated that it began with a 1, but I don't think that's proven. Okay.
It's obviously even.
Yeah, that's fair. And we actually know about its. There are algorithms to calculate its last digits. So you can see, like, here's the last 100 digits. Actually, they've been calculated. I've seen it to 100,000. The last 100,000 digits. So these have been done. There's nice algorithms for working this out, and they're not too expensive.
So what's the actual last digit? 6.
56. They always end in 56. These guys. If you've got 2 inside lots of triangles, it'll end in 56. Okay, so which is important for what's going to come later. So it's I think it's proven to be apocalyptic. So it's got 666 living in it. Yeah, so that's mega. It has some, closely related cousins. It has a triton. Well, you can probably guess. A mega is a 2 inside a circle. A triton is a 3 inside a circle. Okay, so that's a triton.
What about a mega inside a circle?
Well, Brady, you're too fast for these things. Okay, Just stop.
I've been hanging out with you too long.
yeah. But we're going to be better than that. Okay, there's another one that Steinhaus talks about, which is a megiston. Okay, so a megiston is, and you can think about how what these things are. Is circle 10. Okay, so that's a 10 inside 10 squares, and then you can sort of reiterate what that means in terms of triangles. Huge. These are massive numbers, obviously. Okay, so, but now we need to turn on the boosters, Brady, because this is obviously Numberphile, so why wouldn't we?
You want another bit of paper?
Enter Leo Moser, who is an Austrian mathematician. I think this is generally credited to him, but I think the actual source hasn't been identified. And actually, Brady, you totally anticipated it. So you said, why did we go to a circle? Why didn't we just go to a pentagon? Well, this is exactly what Moser thought, okay? So we built the triangle, we built the square, and rather than go to a circle next, we're actually going to define the next step to be a pentagon. So Moser would have defined a mega to be, rather than being circle 2, he defined it to be pentagon 2. Okay?
Nice pentagon. I'm not good at drawing pentagons.
Yeah, good pentagon, yeah. So this obviously means a 2 inside two squares. Okay, so just exactly the same definition as Steinhaus had for a circle 2. So it's a natural way. So you start with triangles, you then define squares as layers of triangles, then you define pentagons as layers of squares. So more generally, if we define the pentagon, you put me under pressure now, and I've done a rubbish one. Okay, so this just means n inside n squares. Okay, but now obviously, now that you've developed this, then you can naturally start to build. So what's a hexagon? Well, it's kind of obvious. This is going to be an n inside n pentagons. And so obviously we're going to get much bigger numbers this way, right? Actually, we hit another cool number. So what's hexagon 2? Okay, this has a name. It's called Iuga. This is Googologists, this is the kind of stuff they come up with. It's called Iuga, which is an amazing name, I think. So obviously, this is another thing that you anticipated, this is obviously a 2 inside 2 pentagons. Okay, so we draw our 2 pentagons. Am I going to do this right? Yeah, like so. And of course, pentagon 2 is mega. So this is exactly what you asked me about earlier, Brady. This is mega inside a pentagon, right? So this is big. This is very, very big. Any question you can go on and figure out what it is. So this is called Iuga, but none of this is anywhere near Mosa, which is the next number I want to tell you about. Okay, so to find the Mosa, we have to sort of iterate this process up, right? So what we're going to say is that we're going to define an n plus 1 gon. Okay, so that's an n plus 1-sided shape of n. Okay, to be an n inside n n-gons. Okay, so if you like, right, if n were here, if n were 3, this would be n inside n triangles, and that would be a 4-gon, which is, of course, a square. So this is the polygons, right? So you've got, so an n-gon is a side with, polygon with n sides. Okay, so 3-gon would be a triangle, a 4-gon would be a square, a 5-gon would be a pentagon, and so on, right? So an n-gon is just a polygon with n sides. So the way, you can see already that this is how we've built it up, that an n plus 1-gon is an n inside n n-gons. Now we're ready to define the Mosa, okay? Named after Mosa, obviously. Okay, so what is a Mosa? This is going to blow your mind, Brady. This is huge. Okay, so we've now defined this process, and we can build up the number of sides of the polygon, and then use that to build up bigger and bigger numbers. Mosa is going to take the number of sides of the polygon he wants to play with to be mega. Okay, so he's going to define it to be megagon.
A megagon.
2, yeah. Okay, so if we want to draw that, well, there's no way we could draw it, but let's sort of pretend to draw it. Okay, that's going to be, we've got some polygon, right? Obviously, and it's got loads of sides. How many sides has it got? It's got mega sides, and we put a 2 inside it. Okay, so you can see that this is enormous. Absolutely enormous. Yeah, I mean, we should sort of, actually, pay some credit to where this actually really started. So whilst Moser and Steinhaus were, in the middle of the last century, actually this entire construction, of course, it wasn't written in terms of polygons and so on and so forth, but essentially this construction of building big numbers in this kind of way actually goes back 1,500 years to ancient India, ancient Indian mathematics. There's something called the Vargita Samvargita, which is exactly this. So it was kind of rediscovered by Steinhaus and Moser, but the ancient Indian mathematicians were doing this back in the day, which is pretty cool. So they were really thinking of some big numbers back then. So what do we know about Moser?
Even.
It is even, of course it's even. And because it's ultimately, this can be reduced down to lots of triangles, actually, a ridiculous number with a 2 inside it. So we know a little bit about its last digits. So for example, we know that it's going to end in 8030156. That can actually be calculated. So what's down here is anybody's guess, but these are known. We have some bounds on it as well. So I'm going to go to another piece of paper. Well, a Moser is certainly no bigger than this number, which is 2 arrow mega to the minus 2, 4, and it's bigger than 2 arrow mega minus 2, 3. Okay, so what does this even mean? So this is this arrow notation again, which we discussed in Graham's number. Every time you add an arrow, you do a repetition of the process below. So this has got, what we've got here is 2, and then there's loads of arrows. In fact, there's almost a mega number of arrows, 4. So these numbers are huge. This shows you how big a Moser is. You can ask the question, which is, I guess, the obvious question that's on all of our lips is, how does it compare to Graham's number? Okay, and it's actually been shown that it is actually, I mean, it was not immediately obvious, but you can prove using this that it's actually much smaller than Graham's number.
Smaller still?
Still smaller, yes. So if you think about, and we can see it quite easily, so if you think about, and this is maybe a bit more for experts, but if we remember when we constructed Graham's number, one of the things we did was we constructed something called G1, which was 3 and then 4 arrows, 3, okay? Well, if you compare this to our bounds for mega, this is actually much bigger than mega. Okay, and then it's because G2, when you construct Graham's number, is 3, and then the number of arrows becomes this previous number on Graham's ladder, like so, then this is obviously bigger than Moser. Okay, because the number of arrows, the number of arrows here, the number of arrows just wins, right? So the number of arrows here is G1, and that's bigger than the number of arrows here, which is around a mega. Even G2, which is, you remember when we constructed Graham's number, we had this number of steps of Graham's ladder where we had G1, G2, G3, each time increasing the number of arrows dramatically, and that turned as, and eventually we stopped at G64, which was Graham's number. So it's very clear, if G2 is bigger than Moser, then G64, which is Graham's number, is certainly bigger than Moser. But we can beat Graham's number, right? So let me just take a Moser up a few notches, a grand Moser. So remember, a Moser was a megagon with a 2 inside. A grand Moser is a megagon with a 3 inside. Okay, we know a little bit about it. It's obviously much bigger than a Moser. It ends in 81627, apparently, but very big number. We can do better. We've got a great Moser, okay, which is megagon 4. It's called a great Moser, ends in 656. But here's a good one, a super Moser.
A champagne super Moser?
Champagne super, yeah. A champagne super, well, I don't know what the champagne adds to it, but let's see. Okay, you probably have to be drunk to think about this. Wow, let me just tell you, this is going to be big. So super Moser. Okay, forget megagons, right? So remember, a Moser was megagon 2, a grand Moser is megagon 3. Forget megagons, we're not interested in megagons. We are interested, Brady, in Mosergons, right? So a super Moser is Mosergon 2. Okay, so it's huge. So the number of sides of the polygon now is a Moser. right? Well, I don't even know what this is, just crazy. Again, but we know something about its final digits, which is amazing, I think, actually. But it's just because this can ultimately reduce to 2 inside lots of triangles. As soon as you've got 2 inside lots of triangles, you can do some algorithms to figure out the last digit. So anyway, it ends in 02061056, always ending in 56. We can do better, okay? So if we've got a super Moser, we can have a super Moser, right? So what do you think a super Moser is?
It's a super Moser gone.
It is a super Moser gone.
Two in there.
So a super Moser has, you have a super Moser gone. So we've got a polygon with a super Moser number of sides and a 2 inside. Crazy. Don't stop there. We can carry on. Obviously, we could have a super Moser. We could have a super Moser. Okay, this is getting silly now. So we'll have a new notation, the hypermoser.
Right.
Okay.
Yeah.
The hypermoser is a super, and so on, mosagon, right? Where the number of supers is itself a Moser, right? And then we put a 2 inside it. Okay, so that's a hypermoser. So it's literally super, a Moser times mosagon.
Okay.
Wow, this is big, right?
Yeah.
I think we can agree that's big.
Yes.
Yeah, it's bigger than Graham's number, I think.
You think?
I'm pretty sure it is.
Do you like having your mind blown, expanding your horizons? After watching that video, I bet you probably do. So why not check out Brilliant, with their amazing range of courses and content covering the world of math, science, computer programming, plenty of good stuff on AI so you can get up to speed with that. Look, I'm glad you watch our videos, but there's no better way to learn than actually doing stuff, interacting with what you're seeing. And Brilliant are the masters of that. This is well designed, it's clever, it's made by humans who also have a sense of fun. That's what I love most about it. And look, I can finally get my head around calculus. This may be the start of your journey to somewhere new and exciting, maybe even a change of career path. To try Brilliant for free, visit brilliant.org/numberphile or scan the QR code there on the screen. There'll also be links in all the usual places, and using them can also get you 20% off an annual premium subscription.
That fast, you still don't have enough time in the age of the universe to have computed one of these things, right? So then you can ask a bit of a random question. Okay, in our patch of the universe, surrounded as we are by the cosmological horizon and an age of the universe, which is 13.8 billion years, right? Okay, we definitely can't, nobody here is ever going to calculate Mega or Moser. Okay, but what if there's some creature somewhere far beyond the observable horizon, right, that has calculated it?